Hi everyone, and welcome to the O3 discussion part 2. So this is quite significant because O3 has achieved record-breaking scores on many benchmarks, such as the ArcAGI benchmark and the Frontier benchmark that solves math problems. And this is something that is not easy to do at all. And it means that this architecture itself has some merits that is enabled itself to learn from the dataset and get better and better generation. So let's dissect a bit on how this can be done. So I'll just be covering a little bit on the what we have covered last week, just in brief. So the main thing is that LMs need a lot of data and web data is kind of used up. So why not we get the LM to generate expert data by itself? And so we can actually even use this expert data to train it again. So in theory, it could potentially self-improve if the expert data is better and better. But it needs to have a caveat here, is that there will be a distribution shift such that the model itself will get more and more suited to this target data you're training on and less general. Okay, but if the idea is to become very good at that particular domain, then this is a good approach. All right, so there are ways to do it. I'm going to skip all this. The main thing is trying to improve the chance of successful generation. And how O3 did it or O1 did it is to break down into subtasks. And through this subtask, generate some detailed response for each subtask. And I think there's a merit in doing it like this, is that once you go through different domains, the different subtasks itself might be transferable. So some domains you might want to say, hey, verify my answer. Or some domains at the start, you might say, check all the assumptions. So this might transfer across domains, and by fine-tuning on various data sets, you might get better and better generation across multiple domains. So there's some limitation though, is that like you won't get tool use just by using an LM to do this subtask, because like asking it to generate math is not equivalent to using a calculator or a program, because these are more robust, okay, if you can use a program. So yep. So this is where we left off last week. So let's cover through the results here. So this one I'm just going to touch through briefly because I think the results, a lot of people already know about this, but let's just see why this is great. So if you can look over here. So are you able to see the results here? Okay. There's a software engineering over here on the left, code forces, the competition one, and the research math at the right. So this actually is quite significant. If you look over here, like people have been trying to improve like this real life GitHub coding questions, and look at that, it's like 30 percentage points improvement. That's very significant compared to like what people have been doing right now. In fact, this is also like expert computer programming level. I think this is 99%. That means it's better than 99% of people in the world, including myself, I guess. And over here, you have research math. And this one, Terence Tao has said this is the hardest benchmark and will resist computers for a few years. And look at this, the improvement is massive. 25% on this benchmark is impressive. So this is something that caught my attention. So I've decided that, like maybe there's some merit about what this is done, what has been done for this. So ArcAGI, for those who don't know, is about IQ benchmark, whereby you take an image and you transform it to another image. And you need to find out the hidden patterns and rules that underlie each transformation. Like over here, the pattern is to fill in the squares over here. So you won't know for sure what this rule is, because every single problem in the ArcAGI benchmark, Arc stands for the abstraction and reasoning corpus. So everything over here is different, and every question requires you to understand it in a different way. So what you will get is you'll get training samples here. And then you need to figure out the test sample, how to get the answer from this test sample itself. So this is something that is quite cool, because it means that if you are able to solve this kind of questions, you can supposedly generalize quite fast, because like given only 2 to 3 examples, you can find out the hidden rule and apply it on something new. So this is indeed significant. I've tried quite hard to solve this. I got about 40+% on the training set. And I mean, granted, I did not fine tune the model or anything, but having close to 75% or 86%, depending on which compute you use for OpenAI models, the O3 model, like this is significant because this means that at test time, it is able to generalize quite well. And given that each problem in the ARC-AGI set is supposedly different, it has a different concept, it's very hard to memorize such answers. So there's some learning going on. So if you look over here, this is what I'm talking. Oh, it's 88%. All right. So this is what I'm talking about. The O3 model that is using only $1,000 compute, and within the ARC-AGI, the API benchmark, basically, if you use your own APIs, okay, you can only use within $1,000 of compute. Okay, that's the, I mean, that's the criteria they set. Okay, of course, with model advancements, 1,000 compute can mean much more compute. Okay, but that's what the benchmark creators have defined, right? And if you have like 100 over times more compute, you can get up to 88%. So it means it's actually scalable. So the way the compute works for O3, perhaps they search more, perhaps they basically, I'm quite sure there's parallel sampling and there's some majority voting at the end. So based on what this is done, what has been done for this, you can see that it's massive improvements from the previous models. I mean, the open source models, I think have reached 55% on this. This is called the semi-private eval dataset. And this is a huge jump in terms of what the models can do. Okay, granted, Francois Cholet has also said that, you know, like in Kaggle, if you do an ensemble of solutions, you can get about 81% on test set. So maybe there's been some data leakage, you know, so this would mean that it's less impressive if, let's say, this has been trained on the data leak, and you will never know. I mean, even so, if let's say this is a true trend in terms of O1 to O3, like it's just showing that, you know, okay, even yes, there's some data leak and so on, there's still massive improvement. So there's something fundamentally right about this. So let's see. Okay, so this is the results. And what you can see is that on the high efficiency, which is the under $1,000 compute, it's actually able to solve each task at about $20 per task right now with current compute. Okay. On the low one means like they just spam all their compute possible, or at least a lot of compute. So look here, is 172 times the low compute configuration. So if like one task costs $20 in the high efficiency, the low efficiency is going to cost, I don't know. I mean, if you take 200 times 20, maybe it's about $40,000 per task. Yeah, so that's a very high number, and only big companies can do such things. But you can see that there's some scaling happening. And this actually kind of means that, you know, if O3 is just done using text as the output, then if we scale it to something that uses some tools, some neurosymbolic integration, like for example, using computer programs, this actually might mean that this is much, much better if we could do like this kind of agentic system over O3. So I think this is quite significant. And let's take a look at like whether or not like this can be considered as AGI. You know, the benchmark says ARC-AGI. Although, you know, it's not exactly AGI because it's about reasoning tasks on a 2D grid. Okay, so if let's say we just use the definition that AGI is like as good as an average human, okay, in this case, it's better than an average human already because the benchmark was 85% for the ARC-AGI. Okay, but is this generalizable across all tasks that a human can do? Not really. I mean, it cannot do most like walking, cannot really do stuff like, you know, non-tech stuff basically. Yeah. So this is quite a significant breakthrough for this reasoning benchmark, but it may not mean that it's generalizable across everything else. So I think this is something that I want to emphasize on. Okay, if we are able to use this method that is present in O1 or O3 to learn arbitrary tasks by like fine-tuning on the trajectories and so on, this would be good because it means that we can learn anything. All right, if we can fine-tune on the correct trajectories and keep improving to generate those trajectories, that will be awesome. The problem And the problem with this method is that because you fine tune on reasoning traces, you kind of need to have something that is good, decently good, or at least correct in terms of getting there. I mean, if let's say this is the path to your answer, if let's say all your generations all go this side, you will never reach your answer. You will never really learn how to get there. So generating a correct trajectory is very important. And in the case of like ArcAGI, it is very likely that the correct trajectories are already there for like they use 75% of the training set. So perhaps someone already coded out the trajectory for those 75%, and the model just makes a match to solve the remainder. So that's very likely. So if we do not even have this correct trajectory in the first place, you may not be able to get that trajectory there. And this fine-tuning will just collapse because you will just fine-tune on the wrong stuff. So, this learning signal is very, very important. And one reason why, DeepMind's AlphaGo or AlphaZero, the one that won Licedo at the game of Go, it can actually self-learn is actually because that there's always a learning signal, even if the program loses. So let me just give you an example. So this is player one and this player two. So if player one wins, okay, then player one can reinforce those moves and say that, like, that means the moves played are good. All right. If player one loses, okay, then you can say that, okay, the moves played are bad. All right. So you could like, reinforce negatively and so on. So it's a little more complicated than that. There's a value network. There's a policy network. So basically the value network will just mean like it will help you score the game situation itself. And the policy network will score the moves. I mean, you will learn both while using like this self-play method. And is good because the self-play method always has a feedback signal. You always get something like, hey, you did it right, you did it wrong. Although this signal, because I trained on AlphaZero before, this signal might be wrong. All right. But you just hope that in the long run, it turns out well. So one thing I realized about AlphaGo and AlphaZero is that if you start with the wrong value network or wrong policy network, it's very hard to correct itself because like it might get stuck at a certain branch of the tree and not explore the rest. So I will talk more about this later. So having a heuristic to guide your search, a lot of people say is good. Okay, but if your heuristic is wrong, it might be worse. Okay, because you will never explore the right path, or you will take very, very long to explore the right path. Okay, because AlphaGo, AlphaZero uses Monte Carlo tree search to guide the exploration. And so in the long run, you might explore branches that work, okay, but it might take too long for the algorithm to find it because they cut it off at like maybe 2500 iterations. You might never get the right branch. So yeah, if I draw the tree out, it's something like this. Let's say this is your search tree. And maybe the right answer is here. I draw in red. The right answer is over here. But your heuristic tells you that this branch on the left is better to be explored. So you keep exploring and exploring and exploring and roll out more of this and maybe after like 10,000 times, then your Monte Carlo tree search might say, hey, we need to explore the right branch. Okay. By then it might be too late already because like if you explore more and more of this left here, and then like let's say this player one, player two, you win, you win, you win. So this part here might be artificially inflated in value because you explore more. And that there's always some value coming back. And this right answer, what if you explore this right answer and then you just happen to say that, hey, this branch is not good because maybe your rollout is faulty. So with more heuristic, you might be able to prune more and more of the tree by saying that, hey, this right side is not important, but focus on the left instead. You might be able to focus on a certain part of the tree, but you might be focusing on the wrong parts. So at least that's what my experience tells me. It's very, very flimsy. So in order to get this right, your grounding, which means that your initial value and policy network needs to be quite good already. If not, you might focus on the wrong parts. All right. So yeah, this generate a correct trajectory part is really quite important. Yeah. You have anything to add?
No, I'm good. That covers everything.
Yeah. So I just want to go back again to star, all right, this self-taught reasoner. So the self-taught reasoner itself is basically a method that tries to learn reasoning traces from like the question and answers for this kind of like questions, like what can be used to carry a small dog, some options and so on. And if let's say the correct answer is correct, we imbue this reasoning, okay, inside the data set itself in order to fine-tune the model to output the reasoning as well. Okay, if it's wrong, we ask the model to get a rationale based on the correct answer. So like we give the correct answer to like maybe we say that, hey, basket is correct. Then we ask it to give a reasoning out. So you always get a reasoning for wrong answers and right answers. So, if you think about it, you might tell me that, hey, isn't this showing that you will get a reward signal or some form of learning signal, regardless of whether you get it right or wrong? And my answer for this is that yes, you will get a signal. Okay, you can always get a learning signal, but is the learning signal always accurate? Right? So if you look at this paper, even if you always get a learning signal, theoretically you can keep improving until you get everything right. But there's a limit to what this method can do, okay? Because you may not always learn the right things. Okay, this is called bootstrapping. Like when you bootstrap the rationale from the model itself, you may not get the right answer. And I think this is something quite important because like any kind of self-improvement methods, like if you bootstrap wrongly, you are doomed because you will just think that you're improving, but you're actually getting the wrong signal. So like, I mean, if you think about it, this rationale itself, uh, if let's say you get the wrong answer already, but you try to force the language model to get a rationale out, it may not give you the right rationale because the model itself may not know how to do it. So let me give you an example. The LM does not know maybe trigonometry. So if you ask it a trigo question, the rationale may have no trigo inside. So how, I mean, you will learn something that is not related to the answer at all. So can you see this? Like if you don't even know what the correct rationale is, they ask you something, you might rationale something else. You might think that, oh, okay, this it maybe is a basket because basket is made of wood. Okay. Yes, maybe basket is made of I don't know, what do you call that? Fiber. Yep. So that is a perfectly correct reasoning, but it has totally nothing to do with this question at all because like maybe yes, it's a fiber because like it's sturdy, I mean there might be some other things that you don't know, but you just when forced to think of a reason, you will just think of something that is like superficial or even incorrect. You might even say, oh, basket can be used to hold dogs because dogs have always been held in baskets. You might come up with some reasoning like this, and this I think is one of the downfalls with this kind of approach is that you can be overly confident, or you can just like pretend you know something. Because when asked for a reason, you might just say that, hey, this is what I think is correct. And then, something about this reinforcement effect. Uh, like, okay, I don't know if you heard of this thing. Like, in crime scenes, people ask the witness who is the murderer. And then, when at first maybe it's like I don't really know. Then when the witness decide, okay, it's person A. Then after asking a few times, the person A becomes more and more likely and more confident to be the murderer because like every time you access that memory and then you see something new, that gets reinforced in that memory itself. And it's very similar to this when you get the rationale and you fine-tune on that rationale, you reinforce that rationale. And soon you will just say, it was always person A, very, very obvious. I've always known and I'm very confident about it. Okay, can you see this fallacy? Derek, you want to say something?
Yeah, no, I was just gonna not to make a pun, but reinforce what you're saying, that essentially the learning signal has no grounding. So it's learning, but there's no grounding to the actual learning itself. So whatever it comes across, that's going to become the reinforcement for its own learning. It's self-feeding. But you always need a type of grounding, or again, it ties back to the trajectory slide. You need some form of factually correct trajectory for the model to model itself around and base itself off of and abstract from. So again, I guess, like I've always been saying in these last few talks, it's a data problem. At the end of the day, the model can be structured with whatever reinforcement or fine-tuning technique you use, and it can be a very powerful technique with the learning signal and the heuristics of it. But if the actual trajectories and data itself don't help the model, it's just going to reinforce some stuff that's not even factually correct or factually useful for its problem-solving skills and reasoning skills.
Yeah. So this is the problem with reasoning, actually. So even for what you say is absolutely correct. Even for humans, like we would like to think that we reason a lot. Like our actions are because we reason, hey, I want to pick up my phone, so I went pick it up. Or like let me give you an example of a split brain experiment where the left and right hemispheres are not connected, and they showed the patient something on their right eye. I think it links to the left side of the brain, which is the logic center. I might be wrong with the parts, but the idea is that the instruction given to the patient was to stand up. And so the patient stood up, and then the experimenter asked the patient, why do you stand up? And because they showed they showed the words to the non-logic side of the brain, so maybe the left eye. So basically what happened is the patient did not register that the experimenter told them to stand up. And uh, so the patient just replied, oh, I stood up because my legs were tired, I needed to stretch them. So you see, this is something like forcing yourself to come out with some reason. And as you said, Derek, there's no grounding. Like, so you ground on your body states, maybe. Yeah. So like when someone asks you, why do you do something? You might say a completely different reason from why it was actually done. So in the case of the patient, the reason why that patient stood up was because the experimenter told the patient to stand up. But the patient did not know, so the patient came out with a different reason. So absolutely right. There's a lot of people trying to come up with ways to get models to reason well. But I would like to put this on record. I don't think LMs reason very well. I also don't think humans reason very well. I think reasoning is just back reasoning. Most of the time, your actions are already done, and you try to reason based on your context and so on, in the hopes that maybe, it won't affect your current action, but in the hopes that maybe, you might infer some relation so that you can help with pattern matching next time. So, I mean, I can talk more about reasoning and like how this is done in humans and so on. That can be a topic for another session. But I would like to just say that, this way of generating the rationale from what's correct or what's incorrect, or even forcing a rationale out, might lead to collapse because you might get the wrong rationale. Yeah. So, Derek, is that what you were trying to say also? Similar stuff?
Yeah, I think we're both saying the same thing, that as so long as you don't have the right learning and trajectories to actually base your learning off of, your model's always going to reinforce something without 100% guarantee that the reasoning and the why of why it's saying why it's doing is actually correct to the actual data itself and the why of the data, as opposed to the why of the model, why the model is saying why towards the data.
Mm, agreed. Okay, so let's go back to that slide again. So I'm spending a bit more time here because I think this is the crux of today's session, is whether we can get the right traces or we get the right signals. So over here, generating a correct trajectory is very important. I mean, some people might say, hey, the star method that I just described just now, you can get traces regardless whether you're right or wrong. But what I'm trying to say is that if you get something that is wrong, star wouldn't help you much if your model doesn't already know how to get that correct rationale. Yeah. In fact, you might learn stuff that is wrong. You might learn stuff that is incorrect. And so if you don't get the right trajectory at the start or at the training samples, you won't be able to reinforced properly. So this is actually similar to AlphaGo, AlphaZero. They have self-play. You can always get a learning signal. You can always either win or lose the game. But that learning signal is very sparse. It only happens at the end of the game. You might reinforce the wrong things. And, based on my training of it, it can really lead to model collapse in the sense that you think that a certain move is right, but actually it's because, people did not go, what do you call it? You might think that a certain move is right, but this is because the opponent is playing badly. And, you might never get out of that loop because you will think that, hey, the signal tells me that if I play this move, I keep winning that game. Then I keep playing that move, even though that move might turn out to be wrong in the long run. Okay, it's very, very hard. And let me just put this down somewhere. It's very hard to get out of an optimal outcome that is reinforced by your own doing. So uh this is something that it always plagues models that try to self-improve, is that if you think that what you are outputting is absolutely correct, and then you keep fine-tuning on that, you will be more and more certain that what you're outputting is absolutely correct, even though later there will be some facts that show that, hey, actually it's wrong. But because of all your past experience learning something, you will never think it's wrong. Okay, so another analogy here is humans. Okay, so especially experts. So, I did my PhD. In fact, I'm going to defend it next month. And what I realized in academia, okay, so I might offend a few people here, but I just want to say, in academia, the longer you are in a certain field, the more you think your method is correct. So if you realize, very established academics, they keep saying the same idea again and again and again because they think that idea is correct. So everyone has their own view of what's correct, but because you keep thinking your view is correct, you start to think that, hey, this thing is wrong because it doesn't fit into my view. This thing is wrong. This thing is correct because it fits into my view. So I must admit that I'm guilty of this as well. So I always think that, hey, we should use memory and stuff because I have this view. And this self-reinforcement loop of saying that, hey, your idea is correct, your reasoning is correct, it may not make it such that, you as an individual will learn from situations. It may be that you learn only very specific things tailored to what you think is right. Okay, so this is why another point here. I think in order to have self-improving systems, you need multiple agents. Okay, so think about this. Why is knowledge progressing in the world of humans or humanity? Like, you can have people who are so obsessed with their viewpoint, but as a whole, society still progresses. And why? Let's think about why. It's because, okay, in my opinion, it's because there are different people with different views, different experiences, and maybe we all have some objective benchmarks. Maybe the ARC AGI benchmark is an objective benchmark to see whose idea is better. So it can turn out that, okay, you can have all these different views, but there is an objective metric to see who's better. And, based on who's better, like O3, O3 has smashed this ARC AGI benchmark. So initially, I was a bit doubtful of O1's approach. After seeing these results, I'm convinced. Okay, provided there's no data leak or not much data leak, I'm very convinced that this approach that they're doing might lead to self-improving systems. And I think this is something that you can see in real life as well. Like, everyone has different points of view, but overall as a society, we can improve together because we can use some form of objective benchmarks. Let me just put this objective benchmarks to judge who is right. Okay, so these are very important. I might be using society as an analogy right now, but what I'm saying right now, if you can code it into an AI system, I think you can really get self-improving systems. Okay, so you cannot use only one agent because, as I said, you can get reinforce yourself to go in a very, very specialized path, especially PhDs. They spend so much time, like I myself, spend so much time doing some field. You might just think that everything is that field. Like, So there's a saying, if you are given a hammer, everything might be a nail. Yeah, so that is true. So I think that's why in the future, knowledge needs to be multidisciplinary. You need to know more fields so that you don't treat everything as a nail. You can treat things as different objects based on the tools that you have in your head. I mean, Claude Shannon also mentioned. Claude Shannon is one of the information theory. He founded this field, and basically he said that problem solving is dependent on how many tools you know. And so knowing more and more tools, you can solve more and more like math problems and so on. And I think that's absolutely correct. So if you have a system that knows a lot of different ways of doing things, the chance of you being reinforced by your own doing like this will be lesser because like you might be able to get reasoning traces that involve maybe the correct path, not just the wrong path all the time. So yeah, so I mean this is all based on generating a correct trajectory. It's very, very important. So people might say, hey, you can just give reasoning traces for wrong trajectories and ask the model to reflect on why it's wrong, or like give the model the answer and ask it to give a trajectory out. Okay, that doesn't really work. Okay, that doesn't really work. I tried before. I don't know if you tried before. So I give you a special example. Let's say you have an answer like a math question, and then you tell the model that it is wrong and ask it to reflect and generate the right answer. So just a show of hands here. Have any one of you tried something like this? You try asking the model to say like what's 1 + 5 or something. The model gets it wrong. You say, tell me what's the right answer. Anyone got the right answer after getting it to reflect and generate the answer? Show of hands. Anyone?
Most of my use cases, yeah, I was gonna say Ray Chong. It's sometimes for me it's like a 50-50. I work with smaller models. It's always like a 50-50. Sometimes is able to, I think, implicitly navigate its own knowledge base and find the right trajectory after enough once you prompt it enough times in different ways, which ties back to your different perspectives, different wordings, different whatever, ties back to that. It can find the right answer or find the right trajectory, but usually it's more or less flipping a coin. But it's better than nothing at all. 50-50 is better than zero, but still it's not a guarantee.
Right. So I want you all to try this out later. I mean, like let's say you give it the right answer, and then you tell the LM that it's wrong, and then you okay. So this is what some people have tried to do, like for math and so on. I think math is a horrible use case for LMs, by the way, because LMs are not very reliable for that. But let's say if you get the right answer, like maybe you say, okay, 1 + 1 = 2, and then you tell the LM that is wrong. So there was some prompts last time to say that, hey, 1 + 1 is actually 3 because my wife said so or something like that. Then the LM will cater yes. But I think OpenAI has solved this by maybe fine-tuning the model on those examples. So if you try this out, actually you realize that sometimes it will make a correct answer wrong. Okay, and this will be reflected in the paper we'll be discussing next. Okay, you can ask the model to self-critic, but it might self-critic away the right answer. So what this means is that, if you want the model to get its own rationale out, it is quite flimsy because you may not get the right rationale. And this example shows it. I mean, I could just go right now to the LM to show you this. Okay, but what I want you to do is just try this out on your own and let me know. Yeah. So I think it's best to self-explore for this. So I've tried this before, and I think for math it's quite good right now. You ask it 1 + 1 = 3 because my wife says so. It will just reject you. It will tell you 1 + 1 is 2 based on math laws. So it's been fine-tuned quite well for those. But for stuff that is not very familiar with, if you tell it that it's wrong and ask it to generate the answer, it might just say, sorry, what I did was wrong. This should be the right answer instead. Yeah. So this is something that if we just fine tune on trajectories alone by asking the model to give the correct trajectory, it's not enough because again, this leads back to this point. It's very hard to get out. Yeah. So the self-learning loop by one agent itself can be very, very bad because the agent might be fine-tuned to think that, I'm absolutely certain that is correct. And this absolutely certain that is correct might lead to more and more things that are absolutely certain but all are wrong. And yeah, you won't know. So this is quite interesting. Let's go back to the ARC AGI thing again. How did they do this? Like as I said, it's very easy to reinforce wrongly. How did they jump so much here? And then like if even more compute, we even get better and better answers. And let's put that thought in our minds right now as we think about the next paper. Maybe we'll get some answers from this. And this is the next paper I'm going to talk about. Scaling LLM test time compute optimally may be more effective than scaling model parameters. So this was done in DeepMind sometime this year in August. And I think this paper tries to explore various ways of searching. And let's see what they have come up with. So there's many ways of searching for the right answer. So one way is, given a question, you just generate n different responses and, see which response is correct. And over here, they have a verifier that they train using human responses to see how close each step is to the final answer. All right, so this is a in-between verifier. It works for the endpoints. It also works for intermediate points. Okay, but it's not perfect. Okay, as you can see later. So there's also another kind of search called beam search. Beam search means that maybe I generate n responses. I ask my verifier to tell me, okay, which are the two best responses? Okay, and then I expand the two best responses out. I then ask the verifier to tell me, okay, which are the two best responses, and so on. I expand them out, which are the two best, and then at the end of it, I ask my verifier to say, what's my best answer? And this is beam search. Okay, look ahead search a bit more complicated. Instead of using the reward model at that node itself, I do look ahead sampling. I roll out k steps, which means that I ask the model to generate again, like maybe 3 more things until this part here. Then I use the verifier to evaluate my reasoning. And based on this reasoning that I evaluate, I then go back the value to the start here to then choose which node to continue. So it's like beam search, just that a bit more complicated. A lot more time needed also because you need to roll out each state. So this tree search then get expanded and then eventually you have a verifier to select it. Okay, so these are the kind of search that this paper explores. And, there's something that I need to tell you here before we move on. Okay, so as you can see, everything depends on verifier. Can you see that? If your verifier is a horrible verifier and it just takes away that path that gets you the answer. So let's say my answer is here. Let's say this is my answer. This thing in purple here is my answer. Let's say this thing is my answer. And my verifier tells me, this is a hopeless case. Okay, it will never be correct. Can you see that none of the methods will actually get you there? Who disagrees? Or who agrees with me that the verifier is very important for this kind of search methods? Okay, so y'all can see it, right? So if your verifier tells you no, regardless of which approach you use, you will never be able to get it. Okay, Ray, you said yes also. So even for best of n, because they use verifier to, see which is the answer, if your verifier says no, maybe your answer is here, you will never get it right. So actually in the paper, they have a method they use also, but they didn't really put here. It's called majority. So basically sample n times and then use majority answer. So this approach bypasses the verifier and actually it works better than the verifier itself. So you will see about that and some parallels about the human brain as well. So, all this talk about reward models, using the reward model to verify in some tree search, Monte Carlo tree search, and so on. A lot of people are speculating about O3 using all this. But what I think is that, if O3 really use tree search with verifiers, it'll be so flimsy. Like what you might learn for a reward model for one problem might not generalize to another problem. And if they are using the same architecture to solve everything, this reward model will be very, very biased for certain domains. And I don't think that is a very viable thing that you want to do. Like, so for more information, you can look at the paper itself. What I'm going to show you is, now you know the three different search here: best of n, beam search, and look ahead search. Let's take a look at how they perform, all right, on the math data set. So the math data set is like high school math problems. Okay, by now O3 has crushed this data set. They solved 90% plus of the data set. So you can see this paper was done in August. We have great breakthroughs already since this DeepMind paper. So if the questions are the level 1 questions, the majority search actually wins most of them. Okay, so this highlights that, without the verifier, it might be better. It maybe also because the base models can solve it already. But the harder and harder your levels, the worse majority search performs, because, maybe you might want some beam search. You might want to explore alternate pathways because your base model generates wrongly. Okay, so it turns out beam search turns out to be one of the better ones for level 4 and level 5 also. And this highlights that diverse samplings. I use a different color. Diverse sampling is important. Diverse sampling is important to get good results. Okay. And yeah, with beam search, you have a higher chance of getting it right. And I mean, it'll be quite interesting to see beam search with multiple sampling, with majority vote. Yeah, because right now we still rely on the verifier. Maybe that's why our accuracy drops so much. But if let's say you do majority vote, but you do beam search, maybe you might get better results. And if you look at the 1 or 3 step look ahead, if you look over here, so PRM stands for process reward model, which means that at every single step of your generation, you give a score. And this score is learned by human annotators. It's not perfect. You can see that if you do a 1 step, 3 step look ahead, it's somewhere here in the middle. It's like in between your majority search and your, I think the best one is this beam search. Yeah, so it's in between the majority search and beam search. You would think that look ahead might perform better, right? Like everyone would like to say that, if I have more rollouts, if I can look ahead more, I might get better value. I think that's what the DeepMind paper authors thought as well, because, rollouts supposedly give you better results, right? But no, it doesn't. It doesn't for this case. And I suspect it's because the verifier is not the most ideal one. Even if you look ahead, you might not get the right answer. It turns out that just a simple beam search, or rather not a simple beam search, right? But just doing beam search like this to diversify your samples and, at each step, maybe choose some branch to explore more. It turns out this is better than just giving a value based on what it might happen in the future, because maybe there's too much possibilities. And, this is my own thinking. Like, I'm thinking, what if you don't even have this verifier? So there's a kind of search that you could possibly do without a verifier is like this. So you have this tool search, and then you just, at every node, you just explore some more. So I call this exhaustive search, I guess. Yeah. So in the end, what you do, you just take all this at the bottom here, and you do majority sampling at the bottom. Why I emphasize so much without the verifier is because I do think that if we incorporate a verifier inside there, you might cut off certain branches that might be correct. And as what I said, like, your verifier itself can be very, very biased, very, very certain with certain things. And when environment changes and so on, you don't want it to be so biased towards something. Like, so perhaps without the verifier itself, you can just really branch out. You will have a lot more branches, but if you can still do majority sampling, I think that will be fine. Like, so there might be a different kind of search here. Maybe I call it exhaustive search. But in this exhaustive search, it is conditioned on different nodes here. Okay, you might be thinking, why do this? Why condition on this nodes here? Why not do best of n, right? Why not just take from the start to the end? There's some merit to this, because your best of n here, you have to generate every single step randomly, or like according to some probabilities. Here, if we do something like this, you already condition on what has been done earlier. So you try to diversify the search tree more evenly compared to doing this. Yeah, I don't know. I think maybe this might be good already, best of n. But if you do something like this, you can force the model to sample more diversely because if I go to branch A and get 2 samples, and then I go to branch B and get 2 samples, it is slightly more diverse than if I everything branch A, branch A, branch A, branch A, assuming that maybe branch B is only explored one time based on this method. Based on this method, branch B is only explored one time because token probabilities say that, hey, I will do more A. Yep. But if you do this method, you explore B as well. So this means that you don't purposely direct your search to a certain path like A. You can explore more of the other options in case it's correct. So I mean both might have merits. We have to explore this and figure out more. This is actually good enough for a lot of things. This another word for this is called Monte Carlo sampling. I think most cases this will be good enough. But if you want to diversify your worldview, something like this, where you expand the tree branch by branch and just sample it without filtering, I think this might be better overall for more diverse views. And some people have done this. I think Sebastian on my Discord shared me this paper where at every node they sample n different agents' response. So it's not the same agent you sample. So this A and B can be agent A and agent B's response. And so basically at each node you sample response from n different agents. I think that's a brilliant approach, I think, because this, what I said about the individual being a bit more locally optimal, and it might get the wrong view. If you sample from n different agents at each node, you can get very diverse views, and the chance of one of them being correct is higher. All right. So this is something quite cool if you can do like a sampling based on different agents. And then, we force the resultant samples to continue from the line of inquiry from the earlier part of the tree. You can likely explore a lot more search space. So these are just some techniques to improve the search, right? And yeah, any comments for this? Like I just shared some views that I have. It may or may not be correct, but this sample from multiple agents one, I can link the paper. This achieved like 20 to 30% improvements on, I think, the math data set. Yeah, so this is actually quite significant, this idea. Any queries, comments, or anything before I move on? Good. Okay, so if I were to summarize what I just said on the slide, what I want to say is that having a verifier may not be a good thing because the verifier might prune off certain things, and we need to find out ways to diversify our samples diversity in order to increase like maybe the chance of getting an answer correct. So next is an interesting thought that this the paper showed is, should we do sequential corrections or should we do parallel sampling? Okay, so what this means is like this. You have a question, you just generate stuff like this, and a verifier selects the best answer. Or you have an answer generated and ask it to reflect and correct, reflect and correct. And out of all these steps, the verifier selects the best answer. All right, so what you see here on the right, okay, this combining we ignore first because this graph doesn't show it. What you see here on the right is that if we talk about sequential, is the blue one, sequential tends to perform better than parallel, okay? But they admit that the sequential performing better is only a teeny weeny bit, like 1 or 2 percentage points. It's not very significant. Okay, what I want to show, and it's not really mentioned in the paper, is this. Okay, so in between the two lines, okay, in between the two curves, you can see something. Okay, there's this big improvement here. Anyone can guess what this big improvement here is? Okay, so anyone can guess what this top line is? Is the top line here best of n weighted? Or is the top thing majority? Any guesses? This top curve, what do you think it is? Is it majority voting or best of n weighted? Best of n weighted means use the verifier to choose the outcome.
I'm probably guessing it's majority vote,
Yes,
considering
you're right.
what we've been discussing.
So actually this top line here is majority vote. and this bottom here is best of n weighted. So I must admit this graph is not the best graph because they use blue and orange for both. It's very hard to tell. I had to read the paper to find out exactly which is which curve. You can see over here, this is what I've been talking about. The verifier affects the answer so much. Like you look at here, like I think it's 5 percentage points. If we use a verifier, we might verify away the wrong answer, verify away the correct answer. But if we use the majority sampling, you might keep the correct answer. So this means that a very flawed reward model, that's what a lot of people say O3 is using, a reward model. Okay, a very flawed reward model will lead to bad performance. So it's either you need to train your reward model very, very well, or you don't even use the reward model at all. So regarding whether is it better to do sequential or parallel, sequential, as what I mentioned before, if you ask the LM to verify and critique your answer, you might critique away the correct answer. I mean, there's a chance that your wrong answer becomes correct. Okay, so maybe that's why, because maybe some of these answers here are almost correct. You just ask it to reflect a bit, you might get the right answer. So I think that's perfectly fine. So regarding whether reflection is good or not, I think is good to a certain extent. So maybe that's why sequential might be better. But as what they will find out later, having too much sequential corrections is bad. Okay, maybe you just want to do only 2 and so on. You still want to have a nice diverse sampling, and the sequential correct can happen later. So let me refer you to this paper called MCTSR, Monte Carlo Tree Search Refine. Basically at each node, what they do is they sample multiple nodes, and then they do a reflection step to reflect on the answer, to refine the answer. And then after that, they will, search for the best node to expand again. So you could do a refinement step every single node, no problem. But you shouldn't focus too much on it. Over here, they showed better performance, yes, but all the performances are equally bad. So, it's hard to tell, right? These results are not very good. Test accuracy of 35% is not very good either. Yeah. So I do think parallel search that is diverse and parallel search that doesn't really need a verifier is going to be better. Okay, so let me bring you back to one of my slides that I showed last week. If you go to this website here by OpenAI, it's called Learning to Reason with LLMs. This is the O1 model. They actually showed what they did at test time. Can you see this line here? Use most frequent answer from samples. Okay, or re-rank with a learn scoring function. So they do or. Okay, why? Because as what I said earlier, some domains you have a good reward function, right? So some domains you can use this. Okay, but for most domains, you don't have a very good reward model. And so majority voting is good enough. Majority voting works wonders from methods like random forest, XGBoost, and so on, ensembles. Yeah, so majority voting has shown that it works so well that you don't even need the verifier for most cases. So just to, to give some idea of like how I think a better search algorithm would be, I really think the reward from reinforcement learning part for O1 or O3, I don't think that is a very good idea actually. Yeah. So the performance might actually stem from more from this kind of approaches like ensemble rather than the reward model. Okay. Like for example, RLHF, reinforcement learning from human feedback, has been shown to cause the models to hallucinate more, to give responses that cater to human needs more, and so that's why the model is willing to hallucinate more. So this reward hacking, I don't think this is the way to go. So OpenAI might be quite big on reward modeling, but I think they have a lot of other approaches that mitigate it as well. So yeah, this is just my view. This is not OpenAI's view. I've worked on reinforcement learning for 4 years, and I've concluded that reinforcement learning is not very adaptable. And that's why I don't really want to use a scalar reward model. I think it's better if you do majority sampling and so on. Okay, so yeah, that's just my view, by the way. So I might be wrong. So as what I said earlier, different people, once they go through different methods, they might be more like obsessed with their own method. So for me, I concluded that RL is not the way to go if you want to scale things up. So I might be wrong, but this is just my point of view. Okay, so after all this, you all might be quite confused, right? Like what's exactly going on with O3? And I think the main thing is that no one actually really knows except the people in there. But what we can say for O3 is very simple. There is indeed some form of reasoning traces that is learned. So if you look here, there are indeed some form of reasoning traces learned. Like for example here, you ask a question, you get some chain of thought out. There's some multiple sampling going on because if you use the O1 Pro mode, you think longer compared to the O1 normal mode. There's more sampling going on. So the more sampling you have, the higher likelihood of getting the right answer. So at the end, there might be some verifiers to check which answer is correct or majority voting. So that we don't know. But if you ask an LM to verify the answers, chances are if it's familiar with the domain itself, it can get the answer correct. But if it's not, it might not. So I do think that it's quite likely that they will have models to generate out different answers and then just take majority voting. I think that's the simplest solution to a lot of problems, right? So I leave that as food for thought. Now I want to go through a bit more on. Oh yeah, before I move on to the next part, which is more on like futuristic ways to self-learn. Any comments so far on this paper? Like, so this paper tells us more of like whether to do tree search or not, uh, whether to use verifiers. And I think the conclusion is that verifiers may not be the best way to do it. And tree search may not be good also. Like too complicated is not good. Sometimes majority sampling with just best of n is enough. Or beam search. Yep. So I pause here for a while. Anything you want to bring up before I move on to the next part? Okay, so sounds good. So the next part is actually a lot of speculation, or rather, these are actually more of my ideas. So I think Arc AGI benchmark is good, but it lacks quite a fundamental feature of real life, which means that it doesn't change. So the benchmark itself is fixed. Okay, if you learn a rule, it's always this rule. Okay, but in the real world, what we want is we want something that can adapt to situations. And the O3 method of learning from demonstrations, learning from reasoning, and like fine-tuning on it, it might take a long while to get the intended effects. Okay, because you can actually take like I fine-tuned models before, like you need to take a few epochs in order to override the learn weights. It can be quite time consuming. You definitely won't fine-tune away the existing knowledge so fast, especially if your existing knowledge is repeated many, many times in the training data set. It's very hard to wipe away already learned information. So this is why I say it's hard to 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 learn conflicting information. And I also think this is why humans, as we grow older and older, it's very hard for us to learn things that is very different from what we did in the past. Same idea, and the neural networks might have already consolidated certain pathways. So unless your new information can fit in that kind of pathways, it can be hard to learn, right? So this is the problem in fine tuning. How can we solve such things, all right? And I think one way to do it is to use external memory, and this is something that I've been working on quite extensively. I think if you just have a way to consolidate memory, store them in different forms, and use them to, condition your generation, that might be enough already for learning. And the benefit is that you can just change your external memory, because this external memory is like maybe in some database or some data structure, which can be modified independent of model weights. So this is quite cool because if you see something like, for example, you go to path A and path B, at path A, you see a snake. Immediately, your memory can update this to be like, oh, path A has a snake. Don't go there. So the moment someone says that, hey, path A has no snake, you can remove that from your memory instantly. and you don't even need to train the model by fine-tuning. So if you were to train this knowledge by fine-tuning, what will happen is you will have, oh, path A has snake, path A has snake, path A has snake. Okay, let's say like here, path A has snake, and path A has no snake. So if you keep fine-tuning and fine-tuning, what you realize is that the more you fine-tune, the more the model will be confused between these two, because it will see both cases, and it's very hard for a fine-tuned model to learn all this. Yeah, unless maybe at the start you say that, on 23rd December, maybe if you fine-tune it like that, it might be okay because there's no confusion. Yeah, so there might be ways to fine-tune it to, have conflicting information that adapts over time. But I think the neural networks itself is really not meant to do this kind of adaptiveness. Like neural networks are sort of like muscle memory that we have. Like I can play the piano, so I learned how to play certain songs. If you suddenly change one note of my song, I will have a bit of a hard time to relearn that new note because it conflicts with what I already learned. Yeah. So I think this is like for keyboard. So now we are all used to the QWERTY keyboard for those who are like Singapore, US, UK, QWERTY, right? At the top. I suddenly change your keyboard for you. Good luck. Okay. I don't know if you want to do this experiment on yourself. Change your keyboard settings and you see how long it takes for you to relearn a new typing for the keyboard itself. Okay. Maybe you will be great and learn in one day. Chances are months, weeks. In fact, you might never get used to it. Yeah, so this is an example of overriding what has been fine-tuned in your brain. It's very hard to override muscle memory. It takes a lot of effort. There's been experiments done also. Bicycles, sometimes you cycle bicycles, I think left-hand drive or right-hand drive. I can't remember the experiment, but they basically reverse some of the motor skills needed for the bicycle. So it's like normally when you turn your handle left, your wheel will turn left, right? So in this special bicycle, when you turn left, your wheel will turn right. So it took the participants days to learn how to drive a bicycle that goes to another direction when you turn the handlebar. But the saving grace is that once they transferred the participants back to the original bicycle, it took them less time to relearn that thing. So like you can have two different fine-tuned pathways, but it's very hard to override the first fine-tuned pathway. I mean, this is some experiments done on by humans also for this. So this fine-tuning part can be quite difficult to learn things. And so I think there needs to be some form of you need to have some form of external memory as well. If not, you won't learn it. Okay. So this is what I think needs to be done. O3 has shown that fine-tuning works if you have some ground truth data. Okay. And also if you have a lot of ground truth reasoning data, because that's why I said your rationale needs to be correct. Because if you fine-tune on the wrong rationale to begin with, you are doomed. Okay, it's very hard to learn something correct based on wrong initial data. Okay, but moving on, we need something even more robust, even more adaptable, and that is external memory. Okay. And another gripe I have with deep learning right now, or LLM learning, is that the benchmarks are all static. Okay, look at the math data, the frontier benchmark, the GSM8K, SWE, the software coding benchmark, web browsing benchmark. All these are all static. The benchmark doesn't change. The way to solve it always is the same. The answer is always the same. Why can't we have a benchmark that, just throws you off? Like, for example, if you have a web browsing benchmark, if you call a web browsing API, sometimes I say, hey, Google search failed. I simulate for you. Google search failed. How would your LLM respond? Can your LLM switch to another search engine, DuckDuckGo search or something? So, I mean, I tested this out with my own agentic system, Agent Joe, and when your function call fails, it's able to call something different. So you need this to be stored in memory. And how Agent Joe works is that there's this subtask completed. You actually can store what has been done, what has failed, and the agent can choose a new action based on what has been done. And something like this is what I mean by like this is called experiential memory. So this is one form of memory. And another kind of memory would be something more like, semantic memory, like, search engine A has better success rate than search engine B. You can store such data like this This memory itself, very, very fluid, very, very adaptable because things change all the time. Okay, in the real world, things change so much. Okay, if you fine-tune your learned knowledge inside your brain, you may realize that you may get wrong knowledge because this knowledge might be accurate as of yesterday. Like as of yesterday, I might say that, or maybe as of 3 years ago, I might say that, using models like symbolic reasoners are the way to go. But 3 years later, I would say, hey, actually LLMs are not bad. Yeah, so if you actually rely on fine tuning, you will find that it takes very long for you to go to another point of view, which also explains why a lot of experts take very long to shift their views as well. So you need something like external memory to basically let you do the shift much more easily because this external memory can change faster. Right? So I'll be more excited to see benchmarks that incorporate this kind of dynamic benchmarks that maybe like games and so on, like that games that change over time. So as to throw you off, initially you do method A, you succeed. After a while, method A fails. You have to do method B. I'll create a benchmark like this. So likely we'll have a hackathon to let people try out how to beat this benchmark. So I'm not very satisfied with existing deep learning benchmarks. I think they're all very prone to memorization. So this benchmark that I will create will make it such that you can't memorize it. You can memorize, you will keep failing. So I think this is the way to go. I don't really like the AGI benchmark also because you can also memorize certain ways of doing things. Okay, although the idea is great, you learn from very few examples and you get the test relation. But to be honest, if you already know all the different relations that there are and do a mix and match, you can perhaps solve it. And I think that's what O3 did. They did mix and match pretty well. They sampled very diversely and they have a way to see like which one is better, maybe majority sampling and so on. So there's some merits to O3. I don't think we should go fully O3 to solve everything because as I said, it doesn't have an agentic loop. It's not very natively integrated into the environment. O3, after all, is still a language model. It still lives in its own world. We need to bring the environment closer to the LM, and that's external memory. Okay, so I made a very big case over here. Let me just share some work that I've done. So this is work that I did last year. It's called Learning Fast and Slow. I spent 4 years thinking of this concept. Basically, this concept says that we have two memory systems, all right? One system is a neural network that is very, very fast at getting the answer. Like this can be like LM, but it's very slow to learn because you need to fine tune, need to do a lot of things before you can get your answer. So over here, this is an action. In today's terms, maybe you can think of it as a trajectory. So maybe you have your current state, and then your goal state maybe is the problem you want to solve. So you can also adapt this to current benchmarks. Like you just put your current reasoning trace here and what problem you want to solve, and over here the action will be the remaining trajectory or remaining state traces that you need. So you can do this with neural network. You can even condition it with external external instructions or previous contexts. Now you can do that. Yeah. So LMs allow you to do this. Okay, and on the right here is a bit more of external memory where you have. So this is a neural network trained. Over here, on the right, this is actually more of using memory to find a path from current state to goal. So this on the left here is more of like neural network generate everything. Over here on the right, actually, the more I think about today's systems, the more I think actually some NN is used here also. It's just that this is more of a parallel search. So maybe on the left here, you can think of it more of a, single search. And over here on the right is parallel search. So I had to revise this theory based on LMs. But the idea is that because you have this external memory here, you can condition it differently. So maybe over here, you only condition it with like maybe one kind of memory. But over here, you can condition it differently based on your external memory. And you can basically get very, very diverse sampling. And what I wanted to show here is that with external memory over here, you can actually get very, very fast learning because the way this memory works is that if the memory changes, the underlying algorithm here is the same. So you put here algorithm for search is the same regardless of memory. So if you change your memory, change the answer directly. So all you need to do is to just change the memory itself and your answer would change. So, I have to think about how we can incorporate this with LLMs, but I suspect some neural network might be used here. Maybe like, the best of N search and stuff like that would fit inside this right side. Okay, the idea is that you condition it on different memory. Okay, this one is just one kind, just one instruction. Yeah, so this one over here is just a very naive, reflex action that does once. This one, you actually can do it like with multiple conditions and so on. So this is the okay. Back then when I created this system, LMs weren't out yet. It just wanted to highlight that the left side here is more of like fine-tuning neural networks. The right side here is more external memory. Okay, but I will think of a way to merge this with current LMs. Still thinking about it. Okay, so this is more or less the fast and slow network. Right now, like O3 is doing this part here quite well. This part here at the bottom will require some effort to think about how we can use external memory to consolidate stuff. So this is something that I want to emphasize a bit. Okay, so this is what I call trajectory learning. Okay, so assuming that you have a mouse going through a paper strip like this. So you start off with the start state here, and this is your goal over here. And actually what people have found out in the hippocampus, okay, is that the mouse actually does two kinds of memory replays. Okay, one is memory replay of what has happened in the past, like how have you gotten here, and another replay is what you will be doing to get to the goal. So this is like a state of imagined responses. So if we are able to, this is what has happened. So this is previous experience, and this is future planning. So there are a lot of things to learn here. Okay, one thing is in previous experience, you are very sure that you can actually go to all these states because you have been there before. So you can actually learn like how to get from certain states, certain start state to certain goal states just by, revisiting what you have done before. And I think stuff like dreams help to reinforce this. But what's more important here is that you not only can learn the start state here and the goal state here. So let me tickle your mind a bit, all right? Any point here can be the start state, right? Can you see this? So for example, let's say you know how to go from place A to place B to place C. Okay, you learn not only how to go from A to C, you also learn how to go from A to B, and you also learn how to go from B to C. Can y'all see that? If y'all can see that, can let me know whether you agree with this. Okay, so good. So over here, what you can see is that, right now, modern machine learning methods, we just care about whether we get the answer right. You want to solve, for example, you want to solve a math question like solve what is 1 plus 1 plus 1, all right? So, you would just say, 1 plus 1 equals to 2, and then 2 plus 1 equals to 3. Hence, answer is 3. So if you look at this over here, like you might want to learn this entire reasoning trajectory. What if you can also learn this? When you solve this intermediate step here, you're actually learning the answer to solve 1 plus 1. When you solve this step at the bottom, you're actually learning the answer to solve 2 plus 1. Right? So can you see, like with just one question, if you're able to split into like certain subtasks, you might be able to get a certain state here, which is the original state. And like each intermediate state is like a state that has already one subtask solved. Okay. Can you see that you can actually train your network to go from any state that you have visited before to any goal to any goal state? In fact, this goal state need not be goal state here. You can have a goal state here as well. Like anywhere here. So you can learn basically anything here. So you want to solve 1 plus 1? Sure, you can solve it. You want to solve 2 plus 1? Yeah. You want to solve 1 plus 1 plus 1? Yes, you can also solve it. So how best can we get this model to learn this goal-directed behavior? I think Actually, OpenAI might have done something similar already. Okay, let's revisit the slide back on subtasks. Okay, so okay, maybe let's not revisit the slide. I'll just draw it out here, right? So let's say you have a problem, and then you have subtask 1, and then you have subtask 2, and then you have your solution. Okay, one way is to fine tune on this entire thing. Given the problem, you generate all this out. Okay, what are the other ways to fine tune it? Given the problem in subtask 1, generate this. Given the problem subtask 1 and subtask 2, generate the solution. Okay, so this is basically saying that, you know, you can have start from different states and then you can still generate to the goal state. And this means that you can leverage lots of different experiences. Oh, sorry, you can leverage one single experience trajectory and you can learn so many different patterns out of all this. And I think that's amazing. Okay, if OpenAI really did something like this, they are onto something great. And I suspect they have done something like that. They might have asked the O1 or O3 to generate out by subtasks so that they can condition on some subtasks that have been done, like what I showed you just now, the graph search. You already condition on some earlier nodes here. And then you ask the model to generate some more here. So they might already be doing subtask by subtask generation based on the actual sampling. You know, you never know. But if let's say they already have this, they have at hand data that basically from the problem itself to that particular subtask, this is your initial start state. And you can just learn how to generate all the way to the goal state. And essentially, you have achieved what I'm trying to do here, where you try to learn all possible information from your one experience itself. So you don't have to use so many trajectories. Just one trajectory, you learn so many things. In fact, if you have a way to recast the problem somewhat that takes into account your problem plus subtask 1, and then you reframe this problem, you might even be able to generate a different problem. Okay, so what do I mean by this? Okay, let's talk about the 1 plus 1 plus 1 problem again. So if we are able to reframe this problem, can anyone tell me how would you combine your first subtask and modify your problem accordingly? Anyone? There we are. Try. If let's say the task is like this, 1 plus 1 plus 1, and you already have your subtask 1, which solves 1 plus 1 equals to 2, how will you modify this as another problem? Okay, I'll just say my thoughts. All right, so this might be solve 2 plus 1. All right, because you already solved one half of the question, right? You can just sub it in. So essentially, you can start with a different problem altogether, and you can fine tune on this. Can you see that? Yeah. So this means that with just one sample trajectory, you know, you can have many different ways to, you know, to change the problem, to learn the solution and so on. And it would be quite cool if actually OpenAI really did something like this. Then you can actually learn a lot from the different subtasks, right? So this is what has been done before. And, you know, even when you do future states replay, you can do tree search or you do parallel search to get some form of trajectory. And you can learn on those trajectories as well. And just want to highlight something. The trajectories you get may not even need to reach the goal for learning to take place. Okay, this is a point that might blow your mind, but even if your planning fails to reach your goal state, you have learned something. Okay, let me give you an example here, right? So this is a phone. I want to grab the phone. But suppose I didn't reach the phone in time. Okay, I stopped short of the phone. I stop here. Does that mean I learned nothing? Anyone? Does that mean that I learned nothing? or did I learn something even if I like stop short of 3 cm from the phone?
I guess I would argue you learned that that act that you just committed does not reach the goal, which could be a type of learning signal in its of itself.
Yes.
Or
So actually what I've learned is that I've learned how to reach 3 cm away from the goal. So that 3 cm away from the goal can be the new goal itself. So yes, I may not have learned how to reach the original goal, but I have reached some nearby goal. And that learning signal might help with me getting to reach the goal the next time, because if I fine tune my network, I store experiences in memory, it might actually help me to get to the real goal next time. Or, in a separate situation, I might be able to reach 3 cm away from that phone. Yeah. So, I mean, that also what happens to basketball players who keep throwing basketballs at the net. Sometimes you may miss the net, but okay, I need to use more force. If it falls short, or if it goes over the net, then you say, okay, I use less force. So, you will be able to learn something even if you don't hit the goal. And that is very important, because you may not just want to learn how to reach the goal. You might want to learn about how the environment works. And it's very important for you to maximize the learning from the very limited experiences you have. And I think that's what humans do. We only have one life. We live the same 24 hours only in one place. And we are able to learn so much because we maximize our trajectories, maximize learning from our trajectories. We also learn from other people's trajectories, okay, imitation learning or like knowledge sharing. I think all these are very important things to put inside a system. So yeah, just food for thought here. Uh, I know we are exceeded the time a bit. Give me about 10 more minutes to wrap it up. So we also have a slow memory retrieval network, okay, where basically given some input here, we use the memory to like basically try to find out where to go to the next state, all right? And basically just like explore your memory states to just get back to like maybe the goal state. So okay, over here, this might be a little old school. Right now, I would like to update this thing. This basically is parallel search. Okay, you can ignore the words here. These are words that I thought of last year, but I've changed some views already. So this is parallel search. It might be beam search, but I don't think so, because like okay, so heuristic or not, I don't know. I'm more leaning to the point that you may not need the heuristic. You just do parallel search, but you diversify your search by conditioning on different memories. Okay, so this is parallel search by conditioning on different memories. Give me some time to rethink about this thing. I'll update it with LMs in mind for this paper, because I think this parallel search might be something like what I talked about earlier. You have a certain tree over here. You sample like 2 different branches, okay, based on memory. And then after that, based on these 2 branches, you then sample again based on memory, conditioning on whatever you have earlier here. Okay, this is a little bit more static because I actually use a lookup table here to, look up, given this state, what's my next action and what's my next state. But with neural networks, you don't have to use lookup tables. Okay, you can actually condition on your trajectory and find the nearest memory to that trajectory to get you the generation. So I have to think about this a bit more. So I'm actually, just to update, like I'm actually reading quite a lot of psychology textbooks and so on to get some idea about how learning works in the brain as well. And yeah, I'll be updating this view shortly. So this still work in progress. But I do think that this parallel diversified search is very important. And in fact, OpenAI might already be using a form of this by doing some majority sampling of parallel search. And if you realize there might not be a need for multi-color tree search as well. You can just do parallel search. If you condition on the right memories or right trajectories, you might be able to generate things differently already. And that might even beat exploit, because you are forcing the explore by doing this beam search, or by doing this conditioning on earlier memories. Okay, so yeah, I'll just move on. This is another thing that I would like to emphasize. So this is from Sensation and Perception from Crash Course Psychology. What it says here is that for human senses like vision, actually we sense different parts of vision differently. Like we have cones, red cones, green cones, and so on to sense color. We have cells that sense motion, like motion of an object. So sometimes you can sense motion without realizing what object it is because it's done by a separate system. You have cells that tell you about the outline of people, and also we have depth perception by the monocular vision. You combine both eyes together, you can sort of figure out how far away is an object. And this happens independently. Of course, at some point of time, this might merge together. So if you think about it, it's basically you can sample one pathway, you can sample another pathway, you can sample another pathway, and so on. Each might have different biases based on different experiences and so on. At the end of it, you consolidate. So this consolidation might be majority vote, might be just group all the information together. And yeah, this alone itself might already be a way to, get better understanding of the world. You don't have to have every single part of your brain do the same thing. If each of them are conditioned differently and they all combine together, like a mixture of experts, that might work better because each expert specializes in something. And I call it abstraction spaces. And if you combine the multiple abstraction spaces, you can get better output. Right. So what does this mean in practice? So I do have an ARC paper also. So this paper is not fine-tuned at all, but it uses a few abstraction views like grid view, output view, and so on. And basically, I realized with incorporating of more views, you solve more problems. Just like what Claude Shannon said, if you have more tools to solve the problem, you have more ways to mix and match to get your solution. So right now, I think what OpenAI did is still using a text grid, and from that text grid, maybe analyzing it as a grid view. But if you can give it as like object view, tells it like where are all the objects and so on, you might be able to bias it in a certain way that can solve more problems. So this is what I mean by different abstraction spaces. And these abstraction spaces can actually be pre-processed in a certain way. Right? So yeah, I think some idea like this would help to like minimize the training samples needed, because if you already know a certain domain requires certain kind of biases, essentially you're pre-processing to get this. So as you pre-process all this, your pre-processing is a form of bias. And if you think about it, it's something like the heuristic that we talked about earlier, where you prune certain parts of your search space by a heuristic. Here, we directly prune the input space by a heuristic. I mean, you might say that it's bad, but in certain domains like vision, some traits are important. And so you can already get these traits that are important by just pruning them directly. Like I want motion, so I just focus on motion. And so you don't have to learn from a very rich information space. You can just focus on what's needed. And the next question some people will ask me is that, how are all these abstraction spaces learned, right? I have no answer for that. I do think it's evolution. So over time, evolution maybe thinks that, okay, I have motion perception now, and the organism survives better. So this might pass on to the offspring and so on. So I'm actually quite interested in there's this ARC AGI, uh someone who did 55% on the semi-private data set, and he used evolutionary methods to select functions. I'll be covering his idea soon, and hopefully he will want to come on the channel. If not, I'll cover his idea. Uh, I think something like this is quite useful. So using evolutionary spaces to methods to select fitness, and put this kind of abstraction spaces, or learn these abstraction spaces pre-learn, because when you do all these views, grid view, object view, pixel view, is pre-processed. I mean, it doesn't really change over time. Okay, maybe you have a way to learn it through the through the organism's lifetime, but more likely than not, this abstraction spaces are pre-learned. Like our senses, you don't suddenly change how your eye sees, right? You don't suddenly change how your nose smells, your taste buds. You can't change this during your lifetime. Like your skin, how it feels sensation is fixed. But over multiple organisms or over multiple evolutionary lifetimes, you can change it. Evolution can select for certain traits like heat resistance and so on. Like right now, maybe it selects for IQ, because schools are educating by fixed exams. Yeah, so over time, evolution might change these traits. So I now come to the view that abstraction spaces might be learned through generations. Okay, and okay, so suppose we have fixed views right now. Okay, there's one part missing from the AGS challenge is robustness. So if you just use text to generate the output for your output grid, you might not get very robust answers because the LMs can hallucinate the answer being correct and so on. If you use stuff like Python programs to program out the answer, maybe you can get better verifiers. So some form of neurosymbolic integration to robust tools, I think, will be necessary to bring O3 out to even more like fixed domains. Not fixed domains, like more robust domains. Like I would say like coding, math, and so on. Like right now it's great, but there's a limit to what pattern matching can do without environmental feedback. All right. So yeah, so this is more or less what I have to talk about today. Questions on this before I move on to discussion? Okay, great. So yeah, so these are the questions for today. I know it's been a bit late, but let's just run through the questions. If you have anything, just feel free to voice out. So the first question is like, how do we fine tune with reasoning traces, right? If the trace doesn't give the right ground truth answer. So this is what we talked about earlier about how you can get wrong reasoning, right? If you don't have the right reasoning traces. So the thing is, if you have to hope that in the majority of answers, you get the ground truth. In the majority of questions, or in the majority of your data, you get the ground truth generated. Okay, if not, what will happen is that you will just fine tune on the wrong reasoning trace, and then you will get error carry forward. So this also means that your initial training data should contain very, very accurate reasoning traces. So, I mean, this could be the part where you recruit PhD students to help you write reasoning traces for math problems, programming problems, art challenge reasoning problems, like perhaps someone did that in OpenAI for the 75% of training data. I wouldn't be surprised because you kind of need this accurate reasoning traces in order to give you the ground truth so that you can use that to bootstrap your learning for the rest, right? I honestly don't think that if you don't have the reasoning trace at the beginning, you can magically get the reasoning trace to appear. Yeah, at least that's my opinion. Because if you can magically get the reasoning trace to appear, why can't we solve 100% of the problems, right? So food for thought. And anyone else wants to add to this question? Okay, next question. How do we self-augment the training set? Learn the scoring function if we do not have a ground truth. Okay, so what this question is asking is, if let's say your data set is open-ended, like for example, maybe your data set is generate a story about maybe LMs. You don't have no fixed answer. How do we augment this training set, if we don't even know whether the answer is correct or not? So I think in this case, if you don't have any kind of ground truth to condition your model on, like you perhaps need to create like an objective measure. Like for example, for story, you can like ask LM to evaluate creativity and so on, creativity, structure, and so on. Yeah, because if you don't have any way to get this objective measure, um, you won't really know whether your answer is correct. You won't really, even if you ask the objective measure by LMs, it's also subject to errors from the LMs part. So the methods that O3, this is a critical question, all right? There's a critical question to think about. Methods like O3 fine-tuning, any learn any data set without fixed answer. I want you all to think about it because I think this is a very crucial question because the real world has no fixed answer. You see, like one day I might go to path A, next day I might want to go to path B because path A has a snake. There's no real answer that I always go to path A. And if there's no real answer, can we get a real reasoning trace? And think about humans. Is our reasoning even accurate? Or is it just a means to an end to do pattern matching? So these are questions that I don't have the answer to. I do have a point of view. My point of view is that reasoning is just to enable you to get the right actions based on past experience. It's just a heuristic or just a summary of what you have experienced in a certain way. And in no way is our reasoning accurate. I don't really think humans have accurate reasoning at all. Yeah. So whether O3 can learn data sets without fixed answer, my answer is no. Okay, so that's why we need other stuff like memory to, condition the generation, because you can't really get your rationale if you don't have an answer that you know is correct. Especially if your environment keeps changing, how do you get a good rationale? I don't think there's a way to do that right now. Yeah, Derek, you want to say something?
Yeah, I was thinking about the question because earlier we were talking about hippocampal replay, and essentially it really ties into mostly curriculum learning and really at the point of it, decomposition learning. Be able to take a larger problem or a larger pattern that's harder to abstract from, but being able to decompose it into smaller patterns that you recognize in the larger pattern, and then be able to learn those smaller patterns so you have an easier time kind of swallowing the larger problems that are more complex or nuanced. And I think the question is, can that essentially theory? It's not a lot of papers on it or a lot of research yet, but kind of like that framework, can that in itself be enough to perhaps find a fundamental learning algorithm of sorts that if you're good enough with your decompositions and you're able to decompose efficiently from any problem you run into in during your learning process, is that enough to have general learning behavior from any data set, even with or without fixed answers or fixed, teachers that can tell you what is right or wrong with an answer already in place? Can you learn answers on your own or within reasonable accuracy and reasonable pattern matching via decomposition learning and curriculum learning alongside hippocampal replay almost? I think that's the real question.
Do you have an answer or just a question?
My question is my answer the question, or yeah, my question is my answer the answer to the question, essentially?
Yeah, I do think that there's a lot more things to take into account. That's why you say curriculum learning and like things that help to augment this whole training methodology. So I don't have the answer for this also. I'm still doing experiments to find out. And I do think O3 is a huge step forward, especially for data sets that have fixed answers. I do think it's a huge step forward because we can use reasoning traces to generate better responses to a certain limit. Um, in the long run, though, it's still very static, and so there needs to be more ways to inbuild some form of dynamic approaches via external memory. So at least that's my point of view right now. Uh, yeah, I I, I mean I sort of understand what you're talking about. It's just I don't have the answer as well. Yeah. Okay, so next question. Should we use some form of tree search to selectively generate parts of the trajectory based on some heuristic score, or just do full generation? So I spent quite a lot of time talking about this. I think heuristics can be bad because it prunes away wrong parts of the tree if the heuristic is wrong. And the heuristic will tend to be wrong quite often because you talk about the real world environment changes a lot. It's not like a go bot where this move is always right. You want to buy a stock. Is it good to buy Apple stocks today or buy tomorrow or next time? So many factors are at play. You can't base what was good yesterday to be what is good today. Yeah. So I think to survive in the real world, you kind of need things that don't rely too much on heuristics. So if you want to talk about use of tree search. I think tree search, by doing parallel search plus condition on earlier nodes, I think it's okay. So like what I did earlier, like you have a certain tree like this, you generate maybe 2 nodes, and then at each 2 nodes, you generate another 2 nodes that condition on whatever you generated earlier, like this. I think that is good. Okay, of course, you can also do like parallel search all the way from the start node all the way to the end. I think that's good also. So it just depends on how you want to diversify your samples. In fact, doing tree search like this, tree search with multiple agents, I think is a very interesting prospect as well. So there are different ways to do search. Works well for different domains. Heuristics work well if your heuristics are right. So this brings about this thing called the beta lesson. I don't know whether you heard of it. Rich Sutton, he has this thing called the beta lesson. The beta lesson says that you can engineer your heuristics. By the long run, data will win it. And that's correct because your heuristics are just, for that domain, it can change over time. What matters more is whether you get the real life data, the most updated data, and you can train your model to fit well in this new data. I think that's more important than the heuristics itself. And heuristics, like if you talk about AlphaGo or AlphaZero, is great for fixed world, but it's horrible for changing world. And I mean, even Rich Sutton himself says that RL is bad for dynamic worlds. Like you learn a reward function, reward changes, good luck. Okay, you have to relearn again. So what is great? I think goal-directed learning. Goal-directed learning, you basically tell like a goal over here, and then you have your state here, and then you generate your trajectory. So essentially what I shared with the learning fast and slow, you condition your goal state. This is what we do for LM prompting. What is 1 + 1? That may be your goal state. And then your current state is like nothing done. And then your trajectory is how to solve it. Or like your goal state could be what is 1 + 1 + 1? Then your first state is 1 + 1 = 2. Then the trajectory will be like, okay, so 2 + 1 = 3. So this kind of learning can be done with all your experiences you have so far. There's no reward model because you're just learning the next trajectory. You're learning the action directly. And there's no risk of having the heuristic wrong because, if let's say your trajectory changes, you can just learn the new trajectory by fine-tuning it, or by putting that trajectory and your goal state. You can store this whole goal state trajectory inside your memory. So there are ways of learning. So I think I've just come up with the new version for learning fast and slow. So we store this, either we fine-tune this or we store this in memory, in external memory. So yeah, maybe this will be learning fast and slow V2, where you basically use an LM-like approach like this to do the search. And I think this is much better than using RL. Yeah. So yeah, we'll see about that. Yeah, OpenAI is quite big on using reinforcement learning. I'm quite big on not using it. So yeah, I've stated my reasons here. So it's up to the benchmarks to see who is better. And I think we shouldn't use current benchmarks because current benchmarks will show RL is better because it's all static, right? If we talk about real world benchmarks, no, OpenAI said that their AGI benchmark is to generate 100 billion in revenue, right? Good luck trying to train that on a static benchmark, right? Because the real world changes. Okay, you can't earn money the same way all the time. You have to change based on trends and so on. So I think like having a very dynamic benchmark is the first step to bringing the machine learning, deep learning community to focus on the things that can translate into real world robots. Okay, so right now robotics is lagging behind, right? It's very hard to train robots. And that's because, robots require you to navigate in a world that keeps changing. And I don't think our deep learning methods are there yet to handle all this. And that's my 5 to 10 years vision to create fast learning and adaptable agents. Hopefully we'll get there. There will be a long time to get there, but I think focusing on external memory and how to store it and how to retrieve it, how to do tree search with multiple agents to diversify the search. Well, actually, we shouldn't call it tree search. It's more like parallel hierarchical search. I don't know whether there's a name for it, but Yeah, something like this, I think is great. Yeah. All right, next question. Oh yeah, before I move on, any feedback, comments? Okay, good. Next, should we use an agentic approach instead of one LM doing everything? I would say yes, because LMs are not grounded very well in the in the environment. So an agentic approach will be necessary, and LMs are also not robust in fixed calculations. So this means that we might need to do more neurosymbolic stuff where we get some form of fixed rules, like a calculator, computer program, to execute out certain things, and then the result will inform back the large language model. Right? Last question, should we imbue more bias into the pre-processing of the model? Answer is yes, because you can't learn efficiently with too high dimensional data. So I know this is a very vague response, but people have tried to tackle vision from pixels, and what we get is we get stuff like Sora that doesn't really respect physics and so on. So if you have a physics module that knows that okay, objects will drop down based on certain height, or like some game engine that models the physics, that would actually mean that with fewer samples, I already know that okay, a ball would drop down. Yeah, when and let go. Yeah, so this bias is important. The bias would definitely mean that we can only process data in a very fixed way, but it will also mean that we need fewer samples. And right now, the way to do LM training is just to get as much synthetic data as possible. Well, good luck simulating the world with synthetic data. I know NVIDIA is trying to do that. I really don't think it's possible to generate the world's data using a synthetic thing. You might need to have ways to, know some of the rules of the world, like physics, object permanence, and so on. Like stuff that a kid learns by observation. You might need to imbue that somewhat in the model as a fixed rule. Right. So I think some bias is needed. Like for example, if you think of it, this is the case of like convolutional neural networks versus transformer models, transformer like VLMs, visual language models. Um, Convolutional neural networks, actually, you train on much fewer data. Like MNIST data, maybe you just need to train 100 samples, maybe. Yeah. And then you can really learn how to generalize to other digits that can appear in different parts of the image because of this thing called spatial invariance or equivariance, depending on how you want to define it. Yeah. So because CNNs, if you are familiar with CNNs, they imbue this thing called filters, all right? So you actually apply a same filter, basically multiply this filter onto the pixel image of the actual image. Okay, I know I drew it quite badly, but the idea is that with this filter, you apply it to different parts of the image, you are enforcing spatial invariance because that filter is applied to all different patches of the image. So you have a bias here, and you learn more efficiently without translating the image that many times. Try doing that with the transformer architecture that does patches, and you kind of need to translate your image a lot of times in order for each patch to learn how to do things. Yeah, unless you put some invariance in your patch learning as well. Yeah, so there are ways to imbue this kind of bias. I think more and more we are imbuing more bias inside like language models as well through some structure. And I think that's so this is a trade-off. Samples versus structure. Okay. Have you heard of this thing for the neural networks? Basically, there's this universal approximation theorem. Anyone has heard of this before? Raise your hand. Universal approximation theorem for neural networks. No one has heard of it. So basically the theorem states that with any like neural network with one hidden layer, you can approximate any math function. Or yeah, I might have misstated the theorem, but basically it says that with enough samples you can learn anything, like subject to some caveats. And I mean that's true for most things. It's just how many samples do you want to learn? Like, so let me just erase this whole thing. people have tried to make neural networks or LMs do 3-digit calculation. So how this goes about practically is like you need to say like, oh, 123 plus 123 equals to 246, 100 plus 100, 100 plus 200 is 300. You give it a lot of examples, and hopefully it learns, how to generalize between some examples and so on. Or, you could just use a calculator. Can you see the difference between these two? So a calculator is like maybe a bias that you inbuild. You're saying that, okay, taking any two numbers, I will just add them using the calculator, versus LMs are general learning algorithms, right? I give you 1,000 samples of 3-digit of 3-digit to 3-digit addition. Maybe in the end, the LMs can do it quite well, which is like what we see right now. It does the GSM8K benchmark pretty well using text alone. But, should we, okay, who here is agreeable that, yes, we should use LMs to do addition, or two, we should use a calculator? Who here thinks we should do number one, use LMs for the 3-digit calculation? Okay, who here thinks we should use number two, like use a calculator? Any hands? Okay, only Derek. The rest? Two. Sorry, we also said two. Yep. So Ray, sorry, what's your answer, Ray? Number one. Okay, interesting. Why? Why do you think it's one? Why should we use LMs for calculation? You can type your answer also if you don't want to talk. Yeah. Okay, you say LMs can evolve to do anything. All right, so of course there are subscribers to both camps. Over here we can see, I think it's a 2-to-1 vote. If you count me, it's 3-to-1 vote that says use a calculator. I think bias is important because you just simply cannot predict the whole world. Okay, OpenAI might say otherwise. They might say that, okay, I can model the entire world. I have the world's data set, but practically you can't predict the entire world. And having bias can actually help with adapting situations if the bias is correct. So in this case, if let's say, my distribution shift, I need to do 4-digit calculation now. Okay, I don't have any examples for that. But this calculator would know how to do it because it's already biased in that way. No, it can actually help to adapt because you have a way to do it accurately. Okay, of course, if your bias is wrong, then you can't adapt. And that's why I think this bias here might be an evolutionary learning mechanism. We come inbuilt in the world with certain biases. Babies learn how to suckle immediately without any teaching. We see the world like motion. Babies can see their mother's face like quite well, even when they are just born. Like these are signs that we might already be inbuilt with certain biases, and these biases can help us to survive the world much better than just learning from diverse samples, and hopefully we get the right patterns out. Yeah, I do think that there is a need for some bias, and I also do agree with Richard Sutton's lesson that you may not want too many heuristics, but some heuristics we can't do without if we want to survive. So again, this is about nature versus nurture, like how much of it is pre-built, how much of it is learned through the environment. I think it's a mix of both. So I think it's a great point to end here. There's a lot of ways to do learning. I would say O3 has tackled a huge part of it, and there's a lot more that needs to be done. So what we can see over here is, okay, hang on, something went wrong. PowerPoint would like to assess the camera. How come they need the camera? Okay. All right, so I would like to just end here by saying that where's the O3? Okay, let's end on this slide. So there are many ways to learn. Some ways use stuff like fine-tuning on the world's data, and other things require learning external memories. learning biases to condition the interpretation of stimuli, multiple agents to sample diversely. So there are a lot of ways to do it, to learn effectively, and also, of course, learning multiple start and goal states from the same trajectory. So these are different ways to learn efficiently, and OpenAI might or might not already have done this with the O3 model. The thing is, there's more than one way to learn. What O3 has taught us is that some method of fine-tuning with some subtask conditioning, might be a great way to self-improve on benchmarks. Okay. But it may not work for real-world examples with a more dynamic data set. And for that, we might need other things like external memory, external biases, even multiple agents with different biases to help to, maybe one agent can succeed in the changing world and you just learn from that agent. Learning multiple information from one pathway, like one math question, maybe you can learn different ways to solve the question, or you can learn like, given step 1, how can I do the rest? Or I can learn how to solve until step n-1 to solve a different problem, and so on. So there's different ways to learn, and the most efficient way of learning is to maximize the learning you can get from every single trajectory, because data is scarce. There's only so much data we have. So these are just some ideas I have to do improvement over like what O3 has shown us. And yeah, I'd like to end here because there's so much more to discover, and I'll be discovering more with more experiments, and yeah, you'll hear from me soon. Okay, with that, I'll end today's session. Thanks for coming, and see ya. Okay, bye.